So in this section, we're going to look at the classification of PDEs. ODEs are pretty simple. They're just classified by order and linearity. But for PDEs, the relative sizes of the different terms with partials of different types can make it much more complicated. So we'll just stick to second-order linear PDEs, which is what most people study anyways, and where most of the applications are. And the classification very closely follows the classification for conic sections. So a conic section is, in its most general form, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. And so this is a second order polynomial in two variables. Right, and this part right here we call the principal part. And then this part here we refer to as the lower order terms. Okay, and so this is the general form for any given ellipse, hyperbola, parabola, etc. Well, that is assuming that A or B or C, one of those is non-zero. If all three of those are equal to 0, then you just get a line. But anyways, for an arbitrary ellipse, you would have well, let's say B equals 0 and A and C have same sign. So you're looking at an ellipse. Okay, well then by change of coordinates, so maybe the original ellipse is something like this guy here, right? And that's what it looks like with respect to the x and y. However, by changing to coordinates that are more appropriate for this particular curve, like say these ones here, so this will be our c and tau coordinates for this particular ellipse, then so with this change of variables right here, you can write it instead in terms of something that looks like c over a squared tau over b squared equals 1. And that's the standard form for it, right? Okay, so the way that we understand these equations is in terms of the discriminant. And so the discriminant, b squared minus 4ac, that's the part under the square root in the quadratic equation. And it is invariant under rotations and translations of the axes. So the discriminant for both of those ellipses is the same. And so we use exactly this for categorizing PDEs or classifying PDEs. So if we have a second order linear PDE in two variables, we can write it as AUXX plus BUXY plus CUYY plus, and then we have our lower order terms being set equal to 0. At least, I guess, and this is the case for This classification that we're doing right here is for constant coefficients. Okay, so there's classification for other types of PDEs as well, but they are gets much more complicated because the discriminant can change in different parts of the domain and whatever else. So we have three types. So there are parabolic PDEs. Now this is when b squared is equal to 4ac, and in this case you get diffusive behavior of your solutions. They follow the pattern of the heat equation, and it can be converted by the appropriate change of coordinates to something that looks somewhat similar to u tau minus ku c equals, and I'll say q for the lower order terms. You can also have elliptic or elliptical PDE. This is when b squared is less than 4ac, and in this case you get something that's static, so it's not an evolution equation like the parabolic one, or the wave equation for that matter. And in this case, you end up with something that looks like the Laplacian of u is equal to some lower order terms. And then lastly, there's also the hyperbolic PDE. And this is when b squared is greater than 4ac. And in this case, we have solutions that exhibit wave-like behavior. So some signal is propagated, and usually in a manner that preserves the signal, at least to some extent, as it travels. And so then this is where we have a difference of sign on the two quadratic, or sorry, the two second order partials. So then it turns out that hyperbolic can also be transformed into something that looks like a mixed partial being equal to a lower order term. And if you look at the parabolic, I wrote one of the lower order terms there to make it suggestive of the heat equation, but if I hadn't, it would have looked like just a second order derivative equals lower order terms. So if you're thinking about them this way, the key point here is that this is a mixed partial derivative for the wave equation versus this one, which is double for the parabolic case.